Any physical quantity, such as length, mass, or time, is measured and denoted in terms of their standards, called a unit of measurement. A unit is an internationally accepted basic reference standard against which the measurements of any physical quantity are compared. In physics, we deal with many physical quantities and their units. However, very few basic units are required to express these physical quantities. Most physical quantities are expressed in terms of some base quantities. These base quantities are referred to as fundamental quantities. For example, distance, which is a measure of length, is a fundamental quantity. It's the same with time. The other quantities, which are expressed in terms of their fundamental quantities, are called derived quantities. For example, area or volume, which is expressed in terms of multiples of length, is a derived quantity. Similarly, speed is a derived quantity as its measurement depends on distance and time. The units of fundamental or base quantities are called base units or fundamental units. The units of derived quantities are expressed as a combination of base units. Such units are called derived units. Base units and derived units together make up a system of units. A system of units is a generally accepted set of units of measurement. Until recently, three major systems of units were in use in different countries based on the units of three fundamental quantities, namely length, mass, and time. Among these were the CGS system, which stands for centimeter, gram, second, and FPS, which stands for foot, pound, second, respectively. These units are adopted by Britain, and hence the system is referred to as a British system. The third system of units is the MKS system, which stands for meter, kilogram, and second. However, in 1971, the General Conference on Weights and Measures recommended a standard set of units of measurement with their symbols and abbreviations. This system is known as Système International d'Units, French for International System of Units, abbreviated as SI. Currently, SI units are followed globally for all scientific, academic, commercial, technical and industrial purposes. In SI, there are 7 base units for the 7 physical quantities taken as fundamental quantities. Following are the quantities and their corresponding units. Length is measured in meters, denoted by the small letter m. Meter is the length of the path travelled by light in a vacuum during a time interval of approximately 300 millionth of a second. Mass is measured in kilograms, denoted by the small letters kg. Kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures at Sèvres, near Paris in France. Time is measured in seconds. denoted by the small letter s. A second is the duration of approximately 9 billion periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Electric current is measured in ampere, denoted by the capital letter A. An ampere is that constant current which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross-section and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 multiplied by 10 raised to the power -7 Newton per meter length of the conductor. Thermodynamic temperature is measured in Kelvin, denoted by the capital letter K. A Kelvin is a fraction 1/273.16 of the thermodynamic temperature of the triple point of water. Luminous intensity is measured in candela, denoted by the small letters CD. A candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 power 12 Hz, and that has a radiant intensity in that direction of 1/683 watt per steradian. An amount of substance which contains as many basic entities, such as atoms or molecules, in a system as equivalent to the number of atoms in a carbon-12 isotope is measured in mole, denoted by the small letters MOL. Apart from these base units, SI has defined two more units for two supplementary quantities, namely plane angle and solid angle. Plane angle d theta is the ratio of length of an arc of a circle to the radius of the circle and is measured in radian, denoted by the small letters RAD. It is defined as the angle subtended at the center of a circle by an arc of length equal to the radius of the circle. Solid angle is defined as the ratio of the intercepted area dA of the spherical surface, described about the apex O as the center, to the square of its radius r, and is measured in steradian, with the symbol SR. If the magnitude of the intercepted area is equal to the square of the radius, then the solid angle is equal to 1 steradian. SI also retains some units from earlier systems for general use. They are minute, hour, day, year, degree, liter, ton, carat, bar, curie, roentgen, quintil, barn, hour, hectare, and standard atmospheric pressure. For all derived quantities, their units are derived from these base SI units. As SI units use the decimal system, it is easy to convert or derive units from base units in this system. You can easily measure length of various entities using appropriate instruments such as a tailor's tape for length of a cloth, a land tape for length of a building, a survey chain for length of roads, etc. However, lengths to be measured can be as large as distance between two heavenly bodies or as small as the radius of an atom. To measure large distances, we employ an important method called the parallax method. What happens if you look at an object with one eye closed? Its position seems to be moved a little from the original position. If you look at a pencil held in front of your eyes against a fixed reference point on a plain wall, with your left eye closing your right eye, and then with your right eye closing your left eye, you observe that the position of the pencil seems to change with respect to the fixed reference point on the wall. This is called parallax. You may call the two eyes are two different viewpoints, since when used separately, they create different lines of sights. Distance between these two viewpoints or points of observation is called basis. Here, the basis is equal to the distance between two eyes. We use exactly the same method to measure the distance of a distant planet. Instead of two eyes, we view the planet from two different observatories on the Earth at the same time. Let X and Y be two observatories viewing the planet S from two locations on the Earth. Thus, XS and YS are the lines of sight of the planet from the two observatories respectively. Here, the distance B between X and Y is the basis which is known. Thus, XYS forms a triangle. Let beta and gamma be the angles made by the lines XS and YS with the line XY respectively, and angle XSY be theta. The angles beta and gamma are measured while observing the planet with the help of telescopes. As the sum of the angles in a triangle is equal to 180 degrees, and knowing the values of beta and gamma, we calculate the angle XSY between the two directions along which the planet is viewed from these 2 points. This angle, denoted by theta, is known as parallax angle or parallactic angle. As the planet is at very large distance from the Earth, say D, its distance from the two observation points on the Earth, namely XS and YS, can be approximated to be equal. As D is large, the ratio of B to D is less than 1. This implies that the parallax angle theta is very small. Subsequently, we consider X and Y as 2 points on arc of a large circle with its center at S and radius D. By definition of angle, theta is equal to the ratio of the arc length, which is the basis B to the radius of the circle D, where theta is taken in radians. Thus, basis B is equal to d theta. This implies that the distance of the planet D from the Earth is the ratio of B to theta. As we measure the distance of a faraway planet from the Earth, we can also measure the size or angular diameter d of the planet. If d is the diameter of the planet, and alpha is the angle subtended by the planet's diameter at the Earth, we have alpha equal to d by d, or d is equal to d alpha, where alpha is in radians. The angle alpha can be measured from a single location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope from the observation location. For the purpose of these measurements, you must know the conversion of degrees into radians. 1 degree or 60 minutes is equal to 1.75 into 10 power minus 2 radians. 1 minute or 60 seconds is equal to 2.91 into 10 power minus 4 radians. 1 second is equal to 4.85 into 10 power minus 6 radians. That was about large distances. Let us now look at the other side of the coin. That is, smaller distances. To measure very small distances, such as the size of a molecule, we cannot employ devices like a vernier calipers or a screw gauge. Special microscopes need to be used. However, all such instruments have certain limitations in measuring lengths. We can use a simpler method to estimate the size of a molecule. Let us take some oleic acid. Oleic acid is a soapy liquid with large molecular size of the order of 10 power minus 9 meter. To start with, we prepare a 20 cc of alcohol oleic acid solution with 1 cc of oleic acid in it, and dissolve 1 cc of this solution in alcohol to dilute it to 20 cc. This makes the concentration of oleic acid as 400th part of the solution. Next, we take water in a large trough and sprinkle some lycopodium powder on its surface. Lycopodium powder is a yellow tan powder that spreads uniformly throughout the surface of water, forming a thin layer. Then, put 1 drop of alcohol oleic acid solution in this trough. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. By pushing away the lycopodium powder from the point where the drop is dropped on the surface. This makes the circular film of the acid drop identifiable on the water surface. Quickly, we measure the diameter of this circular film to determine its area, A. Let the approximate volume of a drop of solution dropped on the surface of water in the trough be V centimeter cube. As the concentration of oleic acid is 1 by 400 in the solution, the volume of oleic acid in each drop of the solution is V by 400 centimeter cube. Since only 1 drop of solution is put in the water, the volume of oleic acid on the thin film is equal to the volume of the drop, that is, V by 400 centimeter cube. Now that we have the area and volume of the thin circular film, we can get its thickness, T, as the ratio of volume to area. T is equal to V by 400 A centimeter. If we assume that the film is monomolecular, as the concentration is very low, the thickness of film becomes the size of a molecule of oleic acid. We learned how to measure a tiny molecular distance or a massive stellar distance. There are various scales of measurement in this range. A brief chart of the measurable distances is shown here. Some of these units are named for usability purpose, such as Fermi, denoted by small letter f, which is equal to 10 to the power minus 15 meter. Angstrom, denoted by accented A, equal to 10 to power minus 10 meter. Astronomical unit, denoted by AU, that measures average distance of the Sun from the Earth, which is equal to 1.496 into 10 to the power 11 meter. Light year, denoted by small letter ly, which is equal to 9.46 into 10 to the power 15 meter. A light year is the distance that light travels with velocity of 3 into 10 to the power 8 meter per second in 1 year. Parsec, denoted by small letters PC, which is equal to 3.08 into 10 to the power 16 meter.